much for having me. As Erika mentioned, I'm working in the Green Central Asian project, which is funded by the German Foreign Office. And we have two main components in this project. The first one is the research, and the second one is the capacity building. Water is a very important component of the transboundary relationships among the Central Asian countries. Here you can see the freshwater resources per capita in cubic meter per country. So as you can see, countries like Tajikistan, Kyrgyzstan, and part of Kazakhstan receive a large portion of annual precipitation, and they act as water storage in the region, especially over their elevated parts. And the other two countries, Turkmenistan and Uzbekistan, are the so-called downstream countries, which receive water from upstream countries. And if you look at the percentage, so you see that countries like Uzbekistan and Turkmenistan rely highly on the fresh water stored in mountainous areas of the Central Asia, the water which is coming from the upstream countries. On the other hand, Uzbekistan uses 92% of the water solely in agriculture sector, and Tajikistan and Kyrgyzstan, for these two countries, water is playing a major role in providing the energy. So it's indeed a very complex situation in Central Asia, and the transboundary water management is very important for the whole region. Now, on top of this comes the global warming and stresses the water, agriculture, geopolitical system in Central Asia. And the policymakers now are really interested to know which scenarios they might face under different global warming levels. Now let's talk about the problems that we have and the challenges. So the first major challenge to study the climate change in Central Asia is that usually the impact modelers or the policymakers require reliable local climate information, which could not be derived from the usual global climate models. So the global climate models have a so-called coarse resolution, but the impact modelers need more regional information, like at the scale of 10-kilometer resolution. Therefore, another layer of a so-called downscaling or refining of the global models is required to discover the potential climate impacts on each sector, like agriculture or hydrology and so on. The second main challenge is that the open source standard surface observation network in Central Asia is not covering all the important regions. I mean, the mountainous area of the Central Asia. And the record is very short, not long enough. Usually we need at least 30 years of reliable observation data to study the climate evolution or use the data for evaluating the climate models or downscaling efforts, etc. And the third main challenge is forced by the nature of the Central Asian domain. So it has a very complex topography, and it requires implementation of detailed surface physical processes in any climate change assessment. So the elevation basically goes from 0 to over 6,000 meters in Central Asia, and you have lots of valleys and mountains in a very small region. And finally, the number of regional climate impact studies published in international journals are very low compared to other regions of the world. Although Central Asia is affected dramatically by the impact of human-induced warming. If you like, only 0.24% of all the studies regarding climate change address this region. Both old and new IPCC models, CMIP5 and CMIP6, indicate a very significant increase of Central Asian temperature till the end of the century, well above the Paris Agreement limits, which you can see in the left panel. The solid black line shows the Era 5 reanalysis trend. And you see at the end of the centuries, under any of the scenarios you take, we will be at least we're going to have a 2-degree warming with respect to the 1971 to 2000 time slice. And the right panel shows how Central Asian warming broke the warming records in 2022 and of course in 2023, especially over the elevated areas of Central Asia, where we have the so-called tundra climate classification, where we have glaciers, permafrost, and snow cover. As an example of the gap in regional climate modeling, here I compare the number of planned regional simulations for Central Asia and Europe in the so-called CORDEX consortium. These 8 planned simulations for Central Asia was conducted at peak. And as far as I know, there exists no other institutions doing the such kind of simulations for Central Asia to downscale CMIP6 for CORDEX Central Asia. So this demonstrates the gap in investment between the Central Asia and the European countries, although Central Asia might suffer more than Europe. Future climate change scenarios. As an example of differences between the global model resolution and regional model 1, here I show the precipitation during Pakistan flood of 2010. On the left panel, the GCM, and on the right panel, the regional climate model, the Cosmos CLM model. You see that to produce patterns like the one on the right panel, we initiated the so-called dynamical downscaling in Green Central Asian project using the regional climate model Cosmos CLM. You see that there are some regions with daily rainfall more than 100 millimeter in the right panel, the regional climate model output. And but on the left panel, the maximum rainfall of the grid points are around 40 millimeter. And again, here I show the probability distribution function of precipitation for maximum daily values in the right in the red box shown in the map. I hope you see it, this red dashed box. On the left panel, the black line with the stars on it shows the PDF of the CHIRPS dataset, which is based on satellite and in situ station data, and also from GCMs and regional climate models. What is interesting here is that the GCM and reanalysis here era entry. And the GCM MPI ESM 12HR do not show grid points with precipitations higher than 7 per day, but regional climate models, the two CCLMs that we have conducted at peak and the two others from CMIP5, they all show more extreme values than the GCM and even the driving reanalysis data. Not only we use regional climate models, but we also apply the so-called statistical methods and machine learning methods to produce local climate patterns that meet our requirements for regional climate studies. Because, as you know, this dynamical downscaling is computationally very expensive. But the statistical models are a bit cheaper, and you can have more ensemble members and produce a kind of measure of uncertainty. So here you see that the impact of the increasing of resolution from left to right panel for temperature. And you see with higher resolutions now, we see clearly the effect of topography, which was not clear in the original model. But the problem with the statistical models is, first of all, they are not physically, the physical consistency is more or less lost. And usually you downscale in a kind of not a multivariate method, like you take the temperature or precipitation for GSEM and then downscale it via a better observation to a higher resolution. So the interact between different variables is more or less lost, which in a dynamical model, you have more physical consistency. And finally, now that we have produced over 400 years of 3-hourly regional climate simulations, we started to apply deep neural networks to find a mapping, a function that maps the coarse resolution of the GCM to its dynamically downscaled RCM. So imagine that you have two pictures, one on the left with a bad resolution and on the right side with a high resolution for over 400 years and every 3 hours. And we try to train a neural network that can learn from these two data sets and produce a function that maps the bad resolution to the better resolution. And at the end, we also applied this function that we have found to a completely different GCM to see if it can produce RCM-like patterns which produce added value to the GCM, to the original GCM. So here I show there are some results from the dynamical downscaling. What you see on the left panel is the changes of extreme precipitations from the regional climate model simulations for 3 different scenarios, and the changes at the end of the century with respect to the historical period. And in the middle panels, you see the output, the ensemble mean of all CMIP6 simulations, and under 3 different scenarios. So you see that, RCM is producing more details, especially over mountainous areas of Central Asia. And there are also some reductions which we don't see in the CMIP6 ensemble. And of course, on the right panels, I show the ensemble standard deviation to show kind of how, on which regions the models are different from each other. And of course, again, where you have more precipitation over the mountainous areas, Himalayas and Tajikistan and Kyrgyzstan, you have more uncertainty among the different models. So now that we have these two images, one from the GCM, which has a coarse resolution, and from the RCM, we have trained neural network to find a function which maps the middle panel to the left panel. And actually, we trained it on the chain of MPI ESM GCM and Cosmos CLM model. And we applied it on a completely new GCM. It's called ECR3 WEG, and wanted to see if the deep learning method can reduce the error of the GCM. So on the left upper panel, you see the mean average error of the GCM, the new GCM, versus its dynamically downscaled version. And on the right panel up, you see the error reduction. So where it's green, it shows a reduction of the error which has been shown on the left panel. So you see, although we have trained the deep learning on completely different GCM RCM chain, it still is producing some error reduction for a new GCM. So we conclude that the neural network might be able to learn some dynamical processes which connects the GCM to its RCM. And with that, I'm at the end of my presentation, and I've listed names of my team members. We are an ensemble of scientists working on hydrology, on climate, and agriculture, and also political sciences, which are interested in the conflicts that the region might have on their future climate change scenarios.